All right, this is Math 1, Unit 8.1 Notes, and we're talking about exponential growth and decay. So I wanted to review real quickly geometric sequences because geometric sequences and exponential functions are very closely related, and I hope to show that to you right now. So we have the first term of this geometric sequence right here is 10, and the second term is 20. And so on. So we can say that a of 1 equals 10. And we can say the common ratio r, 10 times 2 is 20, and 20 times 2 is 40. So we know the common ratio is 2. So one way we learned to write the explicit formula was a of n. We could find any term called n if we know the first term times the common ratio to the n minus 1. We said first term goes with n minus 1. So if we were to write this, it would be n minus 1 equals 10 times the common ratio 2, sorry, I'm supposed to write 2 in there, to the n minus 1. All right? But I also showed you if we had the initial value. This is the first term, not the initial value. The initial value would be the starting point. Sometimes it might be considered the y-intercept. So if we work backwards, 10 times 2 is 20, so 10 divided by 2 is 5. So in this sequence, we could find the initial value, which could be called a of 0, which is 5. And again, this also might be thought of as the y-intercept. So that's another way you might see it. But either way, if we wanted to write this explicit formula using a of 0, it's a of n equals a of 0 times the common ratio to the n. And the reason we like this is because it's very similar to the the exponential formula. Let me plug in these values. So a of n equals 5 times 2 to the n. And what I want you to see is how closely related it is to this exponential function over here. All right, so we'll get to that exponential function in a minute. Let's look at this second explicit formula for the geometric sequence. Again, this is the first term. So let's work backwards and find that initial value, that y-intercept, or a of 0. So how do we get from 16 to 4? Some might say divide by 4, but remember, in a geometric sequence, we always multiply. So we're going to say instead of dividing by 4, we're going to multiply by 1/4. 16 times 1/4 is 4, and 4 times 1/4 is 1. So if we work backwards to the initial value, instead of multiplying by 1/4, we're going to multiply by 4 and get 64. So if the initial value, a of 0, is 64, and the common ratio is 1/4, then we could write the explicit formula as a of n equals 64 times 1/4 to the n. And again, you'll see how closely that is related to that exponential function. So I hopefully pointed out how closely geometric sequences are related to exponential functions. And again, here's a geometric sequence, and it looks exactly like that exponential function. The one thing you'll see is that we switched out y for a of n and x for n. And over here, we used f of x for a of n and x for n. Remember, f of x and y are pretty much interchangeable in function notation. All right, so now let's just go up. Now that we've showed how closely related they are, let's go ahead and look at these two exponential functions. So first of all, let's go ahead and plug the x values in for x and see what our y value comes out. All right, so if we plug in -2 for x, what we get is, this might be a little small for you, but 5 times 2 to the -2, which gives us 5 times 1/4. And the easy thing to write there is simply 5/4. Let me zoom in a little bit. Maybe that'll be a little easier for you to see. Okay, if I plug in -1 for x, we get 5 times 2 to the -1, which is 5 times 1/2, which is 5/2. Okay, 5 times 2 to the 0 power, well, anything to the 0 power equals 1, so 5 times 1 is 5, and then we have 5 times 2 to the first. 2 to the first is 2, and 2 times 5 is 10. And maybe you can see the pattern now. We're multiplying by 2. So without plugging those in, we know it's 10, 20, 40, and 80. All right. So what I'm going to tell you here is we have our initial value. I'm going to call it A. And we have our, right here, we call this B, and it's either our growth or decay factor. And you'll notice that this B is greater than 1, and it is in fact a growth factor. In sequences up here, you can see we called it R. But when we talk about exponential equations, we talk about our initial value being A and our growth or decay factor being B. And whenever our B is greater than 1, it is a growth factor. And I'll show that to you today, hopefully. All right, let me get that back in there. So A is our initial value. B is our growth or decay factor. And when B is greater than 1, it is a growth factor. And hopefully we can show that right here. All right. So let's take a look at this guy over here, and let's plug in our values for x here. So we have basically 64 times 1/4 to the -2, which turns out to be 64 times 16, which I believe is 1,224. You can check my math. Okay. Then we have 64 times 1/4 to the -1, which turns out to be 64 times 4, which is 256. Then we have 64 times 1/4 to the 0 power. Remember, anything to the 0 power is 1, and 1 times 64 is 64. And now hopefully you can see that what we're really doing is basically dividing by 4. 64 times 1/4 to the first. 64 times 1/4 is 16, and then it's 4 and 1 and 1/4. So here we can see that the initial value A is equal to 64, and B, the growth or decay factor, is 1/4. And you can see that this is actually a decay factor. And what we'll talk about more is anytime our growth or decay factor B is between 0 and 1, it is a decay factor, and that is 1/4 definitely between 0 and 1. Okay, now that we have both of these tables filled out, let's go ahead and graph it. So over here, back to this first one we were working on here, let's take a look here. When I graph it, I know you can't see the table anymore, but hopefully you have yours filled out already. If not, you can stop the video and go ahead and fill that out. But if we go at -2 right here, we're at 5/4, which is right about there. At -1, we're at 5/2, which is basically 2.5. At 0, we're at 1, 2, 3, 4, 5. At 1, we're at 10, so 6, 7, 8, 9, 10. And at 2, we're at 20, so 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So then we're off the chart. So this graph looks like this. Basically, this going in this direction, it'll move closer and closer to 0, but never quite get there. Okay, so here's what we're trying to point out. We want you to be able to recognize an exponential equation, whether it's growth or decay, depending on the equation. And what we're going to learn is anytime this B value is greater than 1, it is a growth factor. So you need to know that. If you look at the table that this created, as X is getting bigger, you'll see that Y is getting bigger as well. That's another indicator of a growth factor. And of course, anytime you see a exponential graph that looks like this, that is definitely growth, meaning as we move from left to right, as X goes from left to right, you can see that Y is increasing in value. So 3 ways to recognize an exponential growth function. our b is greater than 1. Our table, as x is getting larger, y is getting larger, and of course our graph, as we move left to right on the x-axis, the y values increase. Okay, let's go back over here to our exponential decay, and when we see an equation or a function, an exponential function, and we notice b is between 0 and 1, we should know it is a decay. When we look at the table, we can see that x is increasing, but what are the y values doing? They are going down as we move from left to right. And if we graph this real quick, we will see that -1, -2, -1, and 0 off the charts. When we get to 1, we are at 16 right here. At 2, we are at 4. And at 3, we are at 1, and then 1/4. And this is an example of a exponential function that is a decay function. So now we can recognize a exponential function when it's decay. The b value is between 0 and 1. The table, as x increases, y decreases, and as we move left and right on the x-axis, the y values decrease.